Yeah, okay, now I think we are ready to try our hands at the proof of Marchenko-Pastur. We have all those bits and pieces, and we just have to use them and apply them and hope that now we really can change our Stieltjes transform for the matrices in such a form that we get an equation for them, at least asymptotically. So the proof of 4.2 of our Marchenko-Pastur. Yeah, good. Okay, so what is our... So we have our Stieltjes transform. That's the idea. That's what we want to control. And that was, I mean, I already put out the n and the p. So this is n over p, the expectation of the unnormalized trace. And then I'm taking here the sum. I mean, it should be the sum from 1 up to n, but I'm splitting this into the sum where I only sum up to n minus 1 of xk transpose, and then I'm subtracting n times zip, but then I'm missing here the last summand, and so I'm writing this here extra, xn transpose. So I take here minus 1, I have the trace and the expectation. Okay, I mean this p is just because I have here the normalized trace, and this n was because I had the 1 over n here, but then of course I also had to put it here. And I mean I do this because this n over p, this is the gamma. Good, okay, and now I call this here A, and this is my rank 1 deformation of this. So this is the A from before, essentially, and the whole thing I call now B. So this is this A plus, and then I have this transformation, this xn transpose. So this means in this language here the x and the y are just the xn, both of them. Yeah, okay, and then I can use this formula here for this situation for this guy here. So then I get xn transpose b to the minus 1 xn, because b to the minus 1 is really what I want to calculate. Okay, but I'm multiplying it with this xn. I mean, here you see I have the trace, so we still have to see how I can get to this, but let us look on this, because for this we have a very nice formula. So namely this is, by this formula, xn transpose a to the minus 1 xn divided by 1 plus xn transpose a to the minus 1 xn. So this is now really using this formula here for this setting. Okay, and now we also have just seen that in the situation where the xn is independent from all the guys which I have in A, that we really can also say what this is. Okay, I mean this, I don't have the expectation here, but by concentration I know that this guy is close to its expectation, and the expectation we just have seen that this gives us the trace of the matrix. So this here is close to, of course one should then really, if one makes it rigorous, one should see how close and that I can control the mistake which I make. But we have concentration estimates, so we know really the expectation, and the actual value with very high probability is very close to the expectation, and we have control over this. Okay, so this here is then essentially the trace of this matrix here, which is now a to the minus 1, and here the same, divided by 1 plus the trace of a to the minus 1. Good. Okay, so this means we can write this here. Yeah, so what do we have now? We have here, I have written this thing here in terms of the trace of a to the minus 1, and a to the minus 1 is more or less also our Cauchy transform. It's just, instead of it's not Sn, but it would be Sn minus 1, but this is actually very close. So this quantity here is more or less very close in the asymptotic regime to my Cauchy transform. Okay, and so I should see whether it's also, what do I have on this side? Is it close to the, not to the Stieltjes transform? Is it close to the Stieltjes transform? For this I have here the trace, but here I have taken this guy here. And this guy is not so clear what this is, because here the xn is not independent from the b, because the b also contains the xn. So the b contains this. So I'm here I cannot say that this is the trace of b to the minus 1. So for this I have, maybe at the moment it looks not so good, because maybe I don't really know what this is. Okay, but now the next trick is what we have done here. I have split it off in my summing from 1 to n. I have split off the last term, xn. And in this calculation, this shows up here. I could have split off also the term x1 or the term x2 and put all the rest into a. So I would say a is the one where I'm summing over all of them, but let's say x5, and then I'm putting here x5. And then I can do the same, and then I have here the x5. And here I have more or less the same. I mean, the a would not be exactly the same, but for the argument, because by concentration, it doesn't matter which one I take. It will always be this. Okay. So all of them are very close to the expectation, and for the expectation, it doesn't matter whether I take the xn or the x1, because the distributions are all the same. Okay, so this means I have this result here also if I replace the n here by any of the other k's. Okay, and this is good, but let's see. I mean, it's okay. So again, so we also, so we can replace xn here by any other k, by xk for any k from 1 up to n, and do the same argument which I had done before, and then I get that xk transpose b to the minus 1 xk is close to the trace of a to the minus 1 plus the trace of a to the minus 1. Okay, and maybe here I should better take the expectation, because I mean the a in principle depends on the k here, but the expectation of all of them is the same. So maybe let's say I take here the expectation. Good. Okay, and now again, I mean, I also don't know what this here is for any of the k's, but now I'm summing over all of them, and this will getting me closer to the trace again. So oh no, actually, let me see, I'm not summing over them. Or maybe, okay. So I have this here, and now let me see what this is. This actually is a number. Okay, so this is a 1 by 1 matrix, and the 1 by 1 matrix is the same as the trace of the 1 by 1 matrix. It is a trivial statement. I mean, the trace of a 1 by 1 matrix is just the entry of the matrix, which is just the number itself. So I can write this here, if I like, in a very pompous way as a trace of this guy. So it's a trace of xk transpose b to the minus 1 xk. Okay, what is it good to write it like this? It is good because under a trace, I mean, this is now a trace of a product of matrices. And the trace has the property that I can move a matrix from the beginning to the end. So this is the same, so this does not change. If I move, let's say, this guy here, no, let me see, what do I want to move? B to the minus 1. Yeah, okay, let me write it like this. It's a trace of b to the minus 1. No, I want to write it like this. I start here. Xk transpose times b to the minus 1. So I mean, I can change things in a cyclic way. Instead of starting here and running like this, I can also start here and then go like this. So I'm just moving this to the beginning here. So it's the same. The trace doesn't change. I mean, if a trace of a matrix product does not change, even if my matrices are rectangular. So maybe for square matrices, everybody knows, but maybe for rectangular matrices, one really should think about it, but it's still the same. Okay, but now the point is, this is now not the trace of a 1 by 1 matrix anymore, but this is the trace of really, what is this now? This is a p by p matrix. Because this is, I mean, now you see it's the other way around. So this is a p by p matrix, and this is also. And so suddenly this trace here, this is now not a trivial object anymore. So this is a p by p matrix. Yeah, and so we see, so what do we actually see now? That this thing here, that I can write this as a trace. Okay, and I have this for each k, and now I should be summing over the k's. Because that's what I really want in the end. So let me now maybe go back to this. I mean, I have this equation for each k, and now I'm summing over all the equations which I have for all the k's. So I'm taking the sum over this. I'm summing from 1 up to n xk transpose b to the minus 1 xk. And this, I mean, each of this term is equal to this. So if I'm summing this over n terms, I just get n times this here. So this is n times what I have here, the trace of a to the minus 1 divided by 1 plus the trace of a to the minus 1. Yeah, okay, but now this sum here on this side, this is something which hopefully I can deal with. I mean, this side here is okay. I mean, those guys are close to the Cauchy transform. But the other side, maybe that's, we have to see whether this is also treatable. Okay, so I have the sum here is equal to this. But actually, those guys here, I can write as the trace of this, which is the same as the trace of this. So this term here, I can write as as what? As the sum from 1 up to n, and each of those guys I'm writing as a trace of the same thing, but then I can also write as a trace of the other thing. So it's actually the trace of xk transpose b to the minus 1. Yeah, okay. And then, of course, the trace is linear, so this is the same as the trace of the sum of those guys. And then we are coming back to something where we have control, no? Because the sum of those guys, they are close to what we are interested in. Okay, so this is the trace of the sum from 1 up to n, xk transpose b to the minus 1. Yeah, but what is the sum of xk transpose? This is actually up to this guy. This is our b. So b, I mean b is the, so what is a? So I mean b is just the whole thing here. So b is the sum over all xk transpose, over all of them, and then with the change of this. So this, the sum over all the xk's is just a b plus this term here. So this guy here, this sum here is just b. So it's just the b plus this multiple of the identity n times z times the identity. good. But now you see, now it's great, because this b to the minus 1 will just cancel with this b. And here we get the trace of b to the minus 1, which is more or less our, the trace of b to the minus 1, which is close to the Stieltjes transform again. So what I have here is the trace of b times b to the minus 1. This is the identity matrix in dimension p plus n times z, b to the minus 1. Okay, the trace of the identity matrix in p dimensions, this is p. So this is p plus, and here I have n times z, and then I have the trace of b to the minus 1. And this is now good. Now I really are back to the trace of b to the minus 1. This is more or less the same as the trace of a to the minus 1. That's things which I can control, and that's are things which are close to my Cauchy transform. And so what I get from this, so you see, this thing here is the same as going back to all this stuff here as summing this here over all k. Or maybe here actually, yeah? That's where I started. So this guy here, this is by this calculation here the same as this. Okay, so in particular if I divide by n, I get a relation between the trace of a to the minus 1 and the trace of b to the minus 1. And both of them, if n is large, are more or less our Cauchy transforms. So what I get is that maybe this side here, and I divide by n because I also have here an n, so it's p divided by n plus, and then the n here goes away, plus z times the trace of b to the minus 1, that this is more or less the same as what I have here. The trace of a to the minus 1 divided by 1 plus the trace of a to the minus 1. Yeah, good. Okay, and now essentially this is my equation for the Cauchy transform, because both the trace of b to the minus 1 and the trace of a to the minus 1 are more or less my Cauchy transform. Maybe up to doing the coefficients right. So maybe let me just still do this, and then we have our equation, which then maybe we can solve next time. But let me finish with writing down the equation which we get from this. So first of all, the trace of b to the minus 1 okay, so I just erased how we defined the b, but okay, I mean, I think we still know. It was the sum over all those guys minus this. So it's exactly what we have in the Cauchy transform. Only in the Cauchy transform we had the expectation, but by concentration we know that this is close. This is close to the expectation of the trace of b to the minus 1. And this here is exactly our Cauchy transform if I also put in the p divided by n as n of z. Because I mean the p divided by n, that was what I took out of the whole thing in the very beginning. So because I also put in the n here. I mean, I put the n here because I took out an n, and I mean the Stieltjes transform is the normalized trace, and I have to repair this by putting the p here. Good. Okay. Yeah. But you see, this is good. So this means the Stieltjes transform is n divided by p times this trace, and n divided by p is something which we can control asymptotically. Okay. And for the trace of a to the minus 1, I mean it's essentially the same, because a and b, the difference between them is just this small term, and so if I take the expectation on all this, I mean it's the same. So the trace of a to the minus 1 is also p divided by n asymptotically as n of z. I mean in principle I have replaced n by n minus 1 because I'm only summing over over n minus 1 data points, but if n is large, n and n minus 1, there is no difference. Asymptotically, they are very small. They are very close together. Good, okay. And so this means in this equation here, asymptotically, I can replace the traces of b to the minus 1 and of a to the minus 1 by the Stieltjes transforms. And this thing p divided by n, which shows up there, this is my gamma. Or I mean, that's what I'm now defining as gamma. So if I put gamma as p over n, and this, I'm looking on a regime where those go to infinity such that this here is fixed, then what do I have? I have the p divided by n, that's gamma. Then I have plus z times the trace of b to the minus 1, but the trace of b to the minus 1 is again gamma times the Stieltjes transform. So this is gamma times Sn of z, and this is more or less equal or very close to, what do I have on the other side? I have the trace of a to the minus 1. The trace of a to the minus 1 is again the Stieltjes transform multiplied with this gamma. So it's gamma times Sn of z divided by 1 plus gamma Sn of z. Okay, so that's more or less the equation which is approximately satisfied for Sn, for my Cauchy transform of the, in the case where I have a p times n matrix. And now one has to argue that somehow, if I know I have Stieltjes transforms which satisfy this equation, that actually I also have a limit. Those are kind of compactness arguments, which is okay. So okay, so that's we take for granted that one can show that we have a limit if n goes to infinity, and then of course the limit must satisfy the limit of this equation. So actually, so this means I'm just taking away the n here, and I have the limit, and that's an equation for the Stieltjes transform in the limit. Okay, and then of course I should check that this is an equation which it's a quadratic equation which has a solution which we can write down. I mean, usually you cannot write down in general situations you cannot write down the solutions of your equations, but in this specific context you can. It's a quadratic equation, and we get a formula, and then of course one has to check that what I get there is really the Stieltjes transform of Marchenko-Pastur. Okay, but maybe I will say a bit more about this next time. In particular, I will also tell you how, I mean, if you wouldn't know a priori that the result should be Marchenko-Pastur, how you would get, if you only have the Stieltjes transform, how you get from this the density, because that's maybe the more interesting thing. I mean, if I tell you this is density, then you can check by integrating that you get a Stieltjes transform. But if I don't tell you the density and ask you what is the density, and you have the Stieltjes transform, then you should be able to calculate it somehow. And this can also be done. That's the Stieltjes inversion formula, but maybe we do this next time a bit more explicitly. Good. Okay. So I hope we have seen. I mean, this was the main step, and this really, I mean, this shows how you get something concrete from your Wishart matrices. Okay, with a lot of nice small tricks. I mean, everything is nice and so, but you have to know how to do it. It's a bit tricky. In particular, I mean, this with the trace. You take the trace of a 1 by 1 matrix, or you have a number you write as a trace of a 1 by 1 matrix, but then you exchange the order, and then actually it's a trace of another real genuine matrix, and you get something non-trivial out of this. So these are nice little things which, if you know how to do it, it's more or less easy. But if you don't know it, I think you would have struggled quite a bit to recover this. Okay, anyhow, so that's it for today.